Monitoring poverty is a crucial component for achieving Sustainable Development Goal 1 of no poverty by 2030. Thus, accurate measurements of poverty rates are needed to track progress towards poverty elimination goals. We present our work on predicting poverty rates using survey and Earth observation data. Poverty rates are measured by carrying out extensive household and demographic surveys. These surveys could include LSMS or DHS surveys, which are just a few to name. These surveys are used to measure household wealth. Wealth measurements include consumption expenditure, income, and/or asset wealth. Wealth estimates are compared to a predetermined poverty line, such as the national poverty line, where households with wealth measurements below the poverty line are determined to be poor. The poverty rate is then computed as the proportion of poor households given the poverty line. Some challenges with extensive surveys are that a single round over an entire country entails substantial cost. In addition, survey completion rates decrease with survey lengths and the process is laborious. These challenges make it difficult to carry out extensive surveys at scale and with high temporal cadence. As an alternative to extensive surveys, proxy means tests utilize a smaller survey, typically around 10 questions, and learn a mapping of survey responses to the binary poverty indicator. A small set of salient survey questions, possibly administered over the phone, provides a more feasible approach to estimate the poverty rate. In this work, we present an approach to estimating the poverty rate using a small set of survey questions combined with machine learning methods. For geographic area A, we define the poverty rate PR sub A as the proportion of households living below some poverty line PL. This poverty rate PR sub A is set as the weighted average of the binary poverty indicator Y sub I for all households in the region. Given household consumption expenditures HCE sub I obtained from the survey, a binary household poverty indicator Y sub I is assigned by comparing HCE sub I to the poverty line PL. In this work, we develop a model F that estimates the household poverty indicator Y hat sub I as a function of a household's survey responses X sub I and the satellite image features M sub C collected for the cluster C that the household belongs to. We utilize a nationally representative survey of 4,954 households in 528 geolocator clusters. Household consumption expenditures computed from the survey responses are compared to the national poverty line threshold of around $3 per day, where households with expenditures lower than the threshold are classified as poor. Sentinel-2 data is an open-source 10 to 60 meter per pixel spatial resolution satellite imagery product provided by the European Space Agency. The survey period is used as the date query range to find cloud-free images for each of the geolocator clusters. For each location, we select the lowest cloud cover image tile and download a 10 by 10 kilometer crop of 3-band imagery centered on the geolocator cluster. Given the data set, our proposed method involves combining image features with survey variables to estimate the poverty rate. This process includes 3 steps. In the variable selection process, we train a model to predict the binary poverty indicator using all survey variables. Given the learned model, we determine feature importance scores, which are used to identify a small set of salient survey questions for the downstream task. Next, we apply a single-step image featureization method to extract relevant image features. Finally, we combine image features with the small set of survey questions and train a poverty prediction model to predict a binary poverty indicator given the reduced set of survey questions. The predicted likelihoods are used to compute the poverty rate. We measure our model performance on the downstream task by comparing the true poverty rate PR to the predicted poverty rate PR hat. For the image feature extraction step, we select a random set of 20 images from the training image set. Of the randomly selected images, a random set of K 3x3 image subpatches are selected as filters for feature extraction. The process filters are then convolved with all images in the dataset and a ReLU non-linear activation is applied. Next, an average pooling function is applied to the outputs to produce a scalar value for each filter K. The resulting vector is the image features vector, which is used in subsequent analysis. In this work, 128 filters are extracted from images and used for subsequent analysis. By randomly selecting a small set of training images to build filters, this method provides a metric of similarity between images in the dataset and those selected as filters. This image feature extraction step is chosen over training an image-based model because of the data-hungry nature of image models compared to the small number of images in our dataset. An explainable boosting machine model is trained to predict the poverty indicator Y sub I. EBM is a tree-based gradient boosting algorithm that learns from only one feature at a time in a round-robin approach. After training the EBM model, the contribution of each survey variable to the prediction is measured and used to rank the survey variables. Given the survey feature importance scores, the most important survey variables are selected. This process yields a reduced set of survey questions for the PMT. The dataset of 4,954 households is split into train and test sets to ensure out-of-sample performance is measured. 68% of the households are randomly placed in the train set, while 32% are placed in the test set. Household allocation to train and test sets is done such that the poverty rate in each set is equal to the national poverty rate. The test set is only used after the downstream task to evaluate the performance of the reduced set of survey variables in estimating the poverty rate. Both the survey variable selection model and the poverty prediction model in the downstream task are trained with the households from the train set using k-fold cross-validation with k equals 10 and a negative log likelihood loss. A grid search hyperparameter optimization is performed over the learning rate, number of leaves, and interactions. We now present some key results of the work. An important contribution of this work is the inclusion of image features with household survey variables to enhance proxy-means testing. When images are combined with 10 standard PMT questions for Ethiopia, improvements in poverty rate estimation are observed as the error means and standard deviations in the poverty rate decrease from 4.09% to 3.88% and 3.03% to 2.94% respectively. This observation is consistent across the full test set and by urbanization level. We also evaluate performance at the cluster level for clusters in the test set. We show the agreement between the true poverty rates and the predicted poverty rates with and without image features. Here, each point represents a geographic cluster. Adding image features to the standard questions increases the R-square to 0.42 from 0.30 when image features are not used. In addition, we evaluate our model performance as a function of number of survey questions. At 0 survey questions where only image features are used, the poverty rate error is highest, though not much higher than when only 10 survey questions are used. With the addition of a small number of survey questions 10 to be specific, while retaining image features, the poverty rate error decreases from 4.1% to 3.8%. In general, the inclusion of image features consistently improve the poverty rate estimate over using only survey variables. As more survey questions are acquired, a small decrease in the effectiveness of image features in estimating the poverty rate is observed. Thus far, only survey variables have been utilized in the variable selection process. We call this approach the survey-guided approach. To obtain survey questions that may better complement image features in the downstream task, we include image features in the variable selection process and call this the survey plus image-guided approach. We evaluate performance under both variable selection methods and when image features are combined with the small set of survey variables in the downstream task. Inclusion of image features to the survey questions obtained through the survey-guided mechanism further reduces the overall poverty rate errors to 3.81% compared to the inclusion of image features with the standard questions. This suggests that image features, given the set of selected questions, may not be complementary, especially within specific urbanization regions. The survey plus image-guided mechanism performs best in estimating overall poverty rates when image features are combined with the small set of obtained survey variables. The overall poverty rate errors decrease to 3.71%, while the rural poverty rate errors decrease to 0.3%. However, the urban poverty rate errors increase to 1.1%. The improved performance for the overall and rural set suggests that by guiding the variable selection process with both image features and survey variables, complementary survey variables are selected to maximize information for improved performance. Image feature inspection is important to understanding the visual characteristics that are retrieved during the featurization step and how these characteristics relate to survey questions. Here, we show the Pearson correlations between regional survey variables on the x-axis and survey variables that highly correlate with image features on the y-axis. This figure highlights two findings. First, while image features may be correlated with survey variables such as fuel source and cooking material, these correlations emerge because image features capture the underlying geographic differences that the survey variables encode. Secondly, image features from the single-step featurization process strongly encode the differences between urban and non-urban regions. This second observation further explains why the inclusion of image features improves overall estimates of the poverty rate, but does not perform as well within a specific urbanization region. In conclusion, we propose an approach to predicting the poverty rate of a region through the combination of survey variables and satellite image features. We show that the inclusion of image features consistently improves the estimate of the poverty rate over using survey questions alone. We also propose the method for selecting the most relevant survey questions for PMT when image features are available. Our survey plus image guided approach outperforms other survey question selection methods. Additionally, we conducted an interpretability analysis around the visual features extracted by the single-step featurization method. We found that the satellite image features capture underlying geographic differences in urbanization levels, complementing the survey questions for improved estimation of the poverty rate. Overall, we demonstrate that satellite image features provide additional information for poverty rate prediction. This better supports the possibility of using a cost-effective and smaller set of survey variables while preserving performance. Thank you.